Hello, and a very warm welcome to the Snoozy Scientist. I'm so glad you found your way here, to this quiet corner of the universe. This is your time to settle in without distraction. To help with that, you might consider making the video full screen. It's a simple way to let the rest of the world quietly fade away. Whether you're nestled in bed, with the soft weight of a blanket settling over you, perhaps curled up on a comfortable sofa, or simply resting your eyes for a moment in a favourite chair, you're in the right place. This time is for you. Tonight, we're going to take a gentle journey together, a quiet exploration into a force that is at once intimately familiar and cosmically grand. We're going to drift through the story of gravity, the invisible hand that holds our world, and indeed the entire universe together. Now, I should offer a gentle disclaimer. I've poured all my effort into making this exploration as soothing as possible, a soft current to carry you toward rest. However, there is a small chance that the quiet wonders we uncover might be just a little too intriguing. If you find your mind gently captivated rather than immediately drifting off, please don't worry. Think of it this way. At the very least, you'll drift off a little wiser, with a new appreciation for the silent, steady force that keeps you anchored in your peaceful space tonight. If this sense of calm is already beginning to resonate with you, I would be so grateful if you would consider giving this audio a gentle like, and maybe even subscribing to join our little community of curious minds. It helps more sleepy listeners find their way to this sanctuary. And if you feel so moved, I always love to read in the comments where you are listening from. It's a beautiful thing to imagine this tapestry of tranquility we are weaving together across the globe. As always, this recording is created for the purposes of relaxation and gentle learning. It is not intended as medical advice. Please allow yourself to simply be here, to listen and to let go. So let's begin our journey. Let's start with the feeling of your own body. The gentle pressure of the mattress or the chair supporting you. That feeling, that simple, constant, reassuring presence, that is gravity. It's the Earth's way of holding you close, of saying, I've got you. Rest here. It's so fundamental that we rarely give it a second thought, like the air we breathe or the steady beat of our own heart. What is it really? This invisible tether. If you were to drop a small pebble from your hand, you know without a shadow of a doubt which way it will fall. It's a certainty written into the fabric of our existence. But why? What is this pull? It isn't a string or a rope or anything we can see. It is simply a fundamental property of the universe. Anything that has mass, anything that is made of stuff, exerts a gravitational pull. You have a gravitational pull. The book on your nightstand has one. The moon, hanging like a pearl in the night sky, has one. And the Earth, our vast and beautiful home, has a very significant one. Imagine for a moment that the universe is a vast, flat, stretchy sheet of fabric like a cosmic trampoline. Now, if you place a heavy ball, let's say a bowling ball, in the centre of this fabric, what happens? It creates a dip, a curve, a well in the fabric. That bowling ball is our sun, immensely massive and creating a profound well in the fabric of space-time. Now, if you roll a smaller ball, say a marble nearby, it won't travel in a straight line anymore. It will be caught in the curve created by the bowling ball, and it will begin to circle it, following the gentle slope of the dip. That little marble is a planet like our Earth. It thinks it's travelling in a straight line, but the very space it's moving through is curved by the presence of the sun. This is the beautiful and strange idea at the heart of Einstein's theory of general relativity. Gravity isn't a force in the traditional sense, like a push or a pull. It's the shape of the universe itself. Mass tells space-time how to curve, and the curvature of space-time tells mass how to move. It is an elegant cosmic dance. The Earth is simply following the path of least resistance, a straight line through the curved geometry of space created by our sun. And we, held to the surface of the Earth, are following our own straight line through that same curved space, kept securely in its gentle cosmic valley. And so we drift within this gentle cosmic valley, held here not by a rope, but by the very shape of reality. This fabric isn't just space, though. Einstein realized it was something even more wondrous: space-time. A four-dimensional tapestry where the three dimensions of space, length, width, and height, are woven together with the fourth dimension, time. It's a concept that can feel a little slippery for our minds to grasp, and that's perfectly all right. We experience the world in moments, in a linear flow of now, but in the grander architecture of the universe, space and Hester time are inseparable. Think of it like a flowing river. The water moves downstream, that is the flow of time. But within that river there are eddies and currents, places where the water slows down or speeds up. The immense gravity of an object like the sun, or even more dramatically a black hole, doesn't just curve space. It also warps the flow of time. Time itself runs a little slower closer to a massive object. This isn't just a fantastical theory, it's a measurable reality. The GPS satellites that orbit our Earth, for example, are further away from the Earth's centre of gravity than we are. Because they are in a region of slightly weaker gravity, their internal clocks actually tick just a tiny fraction of a second faster than our clocks do down here on the surface. It's an incredibly small difference, a matter of microseconds each day. But if scientists didn't account for this relativistic effect, GPS navigation would fail within minutes, accumulating errors of several kilometres every single day. So the next time you use a map on your phone, you can quietly thank this strange and wonderful wrinkle in space-time. You are, in a small way, witnessing the interplay of space, time and gravity. This idea that massive object moving through the universe can create disturbances in space-time leads to another beautiful concept: gravitational waves. Let's return to our image of the cosmic trampoline. If the bowling ball in the centre were to suddenly move, or if two bowling balls were to circle each other and collide, what would you expect to see? You'd see ripples spreading outwards through the fabric, just like the ripples from a pebble dropped into a perfectly still pond. These are gravitational waves. They are vibrations in the very fabric of space-time, travelling outward from the most cataclysmic and energetic events in the cosmos. The collision of two black holes, the merging of dense neutron stars, the explosive death of a massive star in a supernova. These events are so powerful they send shivers through space-time, shivers that travel across the universe at the speed of light. For decades these waves were purely theoretical. Einstein predicted them, but he was unsure if we could ever build an instrument sensitive enough to detect such a faint whisper from the cosmos. The ripples, by the time they reach us from millions or billions of light years away, are astonishingly small. They stretch and squeeze the space they pass through by an amount far, far smaller than the width of a single atom. Detecting them is one of the most incredible feats of engineering in human history. Imagine two laser beams, each several kilometres long, arranged in an L shape. The light in these beams is perfectly controlled, perfectly measured. If a gravitational wave passes through, it will stretch one arm of the L by a minuscule amount, then while squeezing the other. This tiny, almost imperceptible change is what scientists look for. And in 2015, for the very first time, we felt it. We detected the echo of two black holes, each about 30 times the mass of our Sun, spiralling into each other over 1 billion light-years away. For a fraction of a second, the energy released by their merger was more powerful than all the light from all the stars in the observable universe combined. Yet the sound that reached us was the faintest of chirps, a whisper that told a story of cosmic violence and creation. We had opened a new window to the universe. We had learned to listen to the rhythm of space-time itself. So as you lie here, resting, feel the stillness around you. The air in the room is quiet. The world outside may be hushed, but the universe is constantly humming, vibrating with the echoes of ancient, powerful events. These waves are passing through you right now, stretching and compressing the space you occupy in ways so subtle they are utterly beyond our senses. They are a silent, invisible reminder that we are part of a dynamic, living, breathing cosmos. These cosmic ripples, these gravitational waves, are a testament to the universe's most dramatic moments. Yet their influence on us is so slight, so immeasurably gentle, it requires the most sophisticated instruments on Earth just to notice their passing. And still, there is that other gravity, the constant, unwavering gravity of our own planet. It doesn't feel subtle at all. It is the reason we don't float away into the sky. It is the anchor that gives our bodies weight, our movements effort, and our world a sense of up and down. Long before we could conceive of listening to the echoes of colliding black holes, we were trying to understand this fundamental pull. For millennia, it was simply a given. Things fall. That was the nature of the world. But in the 17th century, a mind of incredible curiosity began to ask why in a new and profound way. That mind belonged to Sir Isaac Newton. There is a famous story which may be more legend than fact, but it captures the spirit of his insight perfectly. The story goes that Newton was sitting under an apple tree, perhaps dozing in the afternoon sun, when he saw an apple fall to the ground. It was an ordinary event, something that had happened countless times before, but in that moment a powerful question sparked in his mind. He wondered, if the force of gravity can pull an apple from a branch, does that same force extend higher? Does it reach the top of the highest mountain? Does it perhaps reach all the way to the moon? This was a revolutionary leap of imagination. To connect the falling of a piece of fruit with the celestial ballet of the heavens was extraordinary. He proposed that the very same force that pulls the apple to the earth is what keeps the moon in its orbit. The moon, in essence, is constantly falling toward the earth. But because it also has a great deal of sideways motion, it continuously misses, forever tracing its graceful path around us. It is a perfect balance between its forward momentum and the Earth's steady, inward pull. From this insight, Newton formulated his law of universal gravitation. It's an idea of beautiful simplicity and immense power. He realized that this force of attraction exists between any two objects with mass in the universe. The law states that the strength of the Earth's gravitational pull depends on two things. First, the mass of the objects. The more massive the objects are, the stronger their gravitational attraction. That's why we feel the Earth's pull so profoundly. It is immensely massive. But we don't feel a noticeable pull from the chair across the room, even though it has mass and is therefore exerting a tiny gravitational tug on you right now. The second factor is the distance between the objects. As the distance between two objects increases, the gravitational force between them weakens, and it does so in a very specific way, following what is known as an inverse square law. It's a term that might sound a little technical, but the idea is quite intuitive. Imagine a simple candle burning in a dark room. The light it casts is brightest right next to the flame. If you move twice as far away, the light isn't just half as bright, it's 4 times dimmer. If you move 3 times as far away, it's 9 times dimmer. The energy spreads out over a larger and larger area. Gravity behaves in the same way. Its influence diminishes with the square of the distance. This is why the sun, despite being unfathomably more massive than the Earth, doesn't simply pull us straight into it. We are far enough away that its pull is perfectly balanced by our orbital speed, keeping us in a stable, life-sustaining orbit. Newton's elegant law was a triumph. It could predict the motion of the planets, explain the ebb and flow of the tides, and calculate the path of a cannonball. For over 200 years, it was the definitive explanation of gravity. It told us what gravity did with incredible precision, but it didn't explain how it worked. How did the sun, millions of miles away, reach out across the vacuum of space and exert this force on the Earth? Newton himself was deeply puzzled by this action at a distance. It was not until Albert Einstein, 2 centuries later, that we were given the next piece of this cosmic puzzle. Einstein didn't prove Newton wrong. Rather, he provided a deeper, more complete context. He revealed the mechanism, the how. Newton saw gravity as a force, a pull. Einstein revealed it to be a consequence of the shape of the universe itself, that gentle curve in space-time we visited a few moments ago. In most everyday circumstances, Newton's laws are a remarkably accurate approximation of what's happening. But when dealing with immense gravity, or the universe at its largest scales, we need Einstein's deeper truth, that we're all just following the quiet, invisible contours of space-time. So we have these 2 beautiful ways of picturing the same phenomenon: Newton's steady universal pull and Einstein's elegant curved space-time. One is a force to be calculated, the other a shape to be navigated. But whichever lens you choose to look through, the effect is the same. Gravity is the great organizer. It is the silent, patient architect of the cosmos. It doesn't just hold us in our chairs or keep the moon as our constant companion. It builds worlds. It gathers stars into brilliant families. It is the force of creation. Let your mind drift back, far, far back in time, past any human history, past the age of dinosaurs, past the formation of our own Earth, back to the infancy of the universe itself. In the moments after the Big Bang, the universe was a remarkably uniform place. It was an immense, expanding cloud of mostly hydrogen and helium gas. A cosmic fog, almost perfectly smooth. Almost. Within this fog there were tiny, near imperceptible fluctuations. Regions where the gas was just a fraction of a percent denser than the area next to it. In this near-perfect smoothness, gravity found its first purchase. These minuscule seeds of density, no matter how slight, had a little more mass. And because they had more mass, they had a little more gravity. And so the slow work began. Over millions of years, these slightly denser regions began to gently pull in the gas from their surroundings. It was a slow, patient process. Imagine dust motes dancing in a shaft of sunlight, slowly, almost imperceptibly clumping together. As these clouds of gas grew, their gravitational pull became stronger still, accelerating the process. They drew in more and more material, growing ever denser, ever hotter, collapsing inward under their own immense weight. At the heart of these collapsing clouds, a protostar began to form. The pressure and temperature skyrocketed to levels we can barely comprehend. And then a moment of alchemy, a moment of true cosmic magic. The pressure and heat in the core became so intense that hydrogen atoms, the simplest building blocks of the universe, began to fuse together to form helium. In that instant, a star was born. A self-sustaining nuclear furnace was ignited, releasing a tremendous amount of energy that pushed outward, finally balancing the inward crush of gravity. A star is a perfect equilibrium, a lifelong dance between the inward pull of gravity and the outward push of nuclear fusion. And the night sky began to fill with light. What gravity does for stars, it also does for galaxies. On an even grander scale, it acted as a cosmic shepherd, gently herding these newly born stones, along with vast clouds of gas and mysterious dark matter, into immense swirling structures. The beautiful spiral arms of a galaxy like our own Milky Way are a visible manifestation of gravity's organizing power, a stellar city built by this silent, persistent force. Every star you could possibly see in the night sky is part of our home galaxy, all of us held together in this grand celestial family by the steady hand of gravity. And this same creative process brought about our own home. Around 4.5 billion years ago, in a quiet arm of the Milky Way, a vast cloud of gas and dust, the remnants of an older star that had lived and died, began to collapse. Perhaps it was nudged by the shockwave from a nearby supernova, a gentle push that started the process. At the centre, the material clumped together to form our sun, but not all the material made it to the centre. A vast, spinning disk of dust and gas was left orbiting the young star, like clay on a potter's wheel. Within this protoplanetary disk, gravity continued its patient work. Tiny grains of dust frosted with ice began to stick together. Electrostatic forces, like the static cling on a dry day, may have helped them get started, but as these clumps grew from pebbles to rocks to boulders, their own gravity became significant. They began to pull in their neighbours, growing larger and larger in a process called accretion. These planetesimals, the seeds of future worlds, collided and merged, slowly clearing their orbital paths over millions of years. And from this slow, constructive, gravitational ballet, the Earth was formed. The ground beneath you, the iron in your blood, the water in the oceans, all of it was gathered together from a cosmic cloud of dust and gas by the patient, persistent pull of gravity. And so our Earth was formed, a sphere of cosmic dust and rock, gathered by the gravity's persistent embrace. But gravity's work was far from over. Once our planet was assembled, this ever-present force began to shape it from the inside out. In its early days, the Earth was a hot, molten world, and in this yarry liquid sphere, gravity began to sort the materials. Imagine a jar of water and sand that you've just shaken. If you set it down and watch, you'll see the heaviest grains of sand settle to the bottom first, while the lighter particles remain suspended for longer. On a planetary scale, the same thing happened. The heaviest elements, primarily iron and nickel, felt gravity's pull most strongly. They slowly, inexorably, sank towards the centre of the planet, forming the dense metallic core. The lighter materials, the molten silicates and other rocky minerals, were displaced by this process, floating upward like oil on water. The lighter material eventually cooled and solidified to form the Earth's mantle and the thin, solid crust on which we live. This process, known as planetary differentiation, is perhaps the most important event in our planet's geological history. It's because of this gravitational sorting that we have a dynamic, molten core that generates our planet's protective magnetic field, an invisible shield that deflects harmful solar radiation and makes life on the surface possible. Gravity didn't just build our house. It gave it a foundation of iron and a protective roof of magnetism. Gravity's influence is just as profound on the surface, especially when it comes to water. It is the ultimate leveller. Every river, every stream, every tiny trickle of rainwater is guided by gravity. It pulls water from the highest mountain peaks, carving canyons and valleys over millennia, carrying sediment on a long, meandering journey that always, eventually, leads downward to the sea. The very concept of sea level is a testament to gravity's power to create a smooth, uniform surface over the vast majority of our world. And it is here, in the great oceans, that we see one of gravity's most beautiful and rhythmic expressions, the tides. As you rest tonight, the oceans are breathing, rising and falling in a slow, steady rhythm. This breath is dictated primarily by the moon. Our celestial companion is close enough that its gravitational pull is slightly stronger on the side of the Earth facing it, and slightly weaker on the side facing away. This difference is enough to pull the water into a slight bulge on the near side and to leave a corresponding bulge behind on the far side. As the Earth rotates beneath these two bulges each day, we experience the gentle rise and fall of high and low tide. The sun contributes to this dance as well, its immense gravity pulling from afar, either amplifying or softening the moon's effect. The tides are a constant, tangible connection, a daily reminder that we are part of a gravitational system tethered to our moon in a silent cosmic partnership. This constant directional pull has been a fundamental force for every living thing that has ever existed. Life on Earth emerged and evolved in a world where down was a constant and up required effort. Think of the quiet strength of a great tree. Its entire structure is a masterpiece of engineering designed to defy gravity. It builds strong, rigid cellulose and lignin to create a trunk that can lift its leaves hundreds of feet into the air, reaching for the sunlight it needs to survive. At the same time, its roots respond to gravity's pull in the opposite way, growing downward, anchoring the tree and seeking out water and nutrients in the soil. This response of a plant to gravity is called gravitropism, a silent awareness embedded in its very cells. And what is true for trees is true for us. Your own body is a living adaptation to gravity. Your skeleton provides a strong, rigid framework, and your muscles provide the power needed to stand, walk, and lift against its constant pull. The simple act of getting out of bed in the morning is a small victory over gravity. This is why astronauts who spend long periods in the microgravity of space must exercise for hours every day. Without the constant resistance of Earth's gravity, their muscles begin to atrophy and their bones lose density. Our strength is, in a very real way, a gift from gravity. It is the force we have been pushing against our entire lives, and it has made us strong. And so this constant familiar force has shaped our planet and our very biology. We are, in every sense of the word, creatures of gravity. It holds our oceans in place, it anchors the roots of the trees, and it gives our bodies a sense of strength and substance. But what would it take to leave? What would it take to slip this gentle, persistent bond, even for a short while, and see our world from the outside? To do so requires an almost unimaginable amount of energy. It requires an effort great enough to counteract the entire gravitational pull of a planet. Humanity achieved this not with strength of muscle, but with strength of mind by harnessing a fundamental principle of the universe. The idea is one that Newton also gave us, his third law of motion. For every action there is an equal and opposite reaction. If you are standing on a skateboard and you throw a heavy ball forward, what happens? You and the skateboard will roll backward. You have pushed on the ball and the ball has pushed back on you. A rocket works on this very same principle, but on a colossal scale. It isn't pushing against the ground or the air. It is pushing against its own fuel. It expels hot gas downwards with tremendous force, and in return, that gas pushes the rocket upwards with an equal and opposite force. A launch is not so much an explosion as it is a perfectly controlled, sustained and powerful exhalation of energy, all for the singular purpose of moving up away from the centre of the Earth. But just going up isn't enough. Gravity is relentless. What goes up must, as we know, come down. To truly break free, a spacecraft must reach a specific speed, a kind of cosmic threshold. We call this the escape velocity. Imagine you are standing in an open field and you throw a ball upwards. It travels up, slows down, stops for an instant, and then gravity pulls it back to your hand. Now, imagine you could throw it much faster. It would travel much higher before returning. If you could throw it with the power of a cannon, it would soar for miles before arcing back down to Earth. Now, picture in your mind being able to throw it with such incredible speed that as it travels up and away, the pull of gravity still weakens it, still slows it down, but never quite enough to stop it and pull it back. It would have enough momentum to overcome the pull and just keep going, sailing out into the solar system, free from the Earth's grasp. That is escape velocity. For our Earth, that speed is about 11.2 kilometers per second. That's nearly 7 miles every single second. It's a velocity so immense it's difficult to truly comprehend. It is the measure of how deep our planet's gravity well is, the sheer amount of energy required to climb out of it. However, most missions into space are not trying to leave the Earth forever. They are trying to achieve something far more elegant, something that is less about escape and more about balance. They are trying to enter into an orbit. And here we return to a beautiful thought experiment, first imagined by Newton himself. Picture a cannon perched atop the highest mountain you can imagine, a mountain that pokes above the Earth's atmosphere. If you fire a cannonball with a small amount of gunpowder, it travels a short distance before gravity pulls it to the ground. If you use more gunpowder, it travels further, its path curving with the Earth before it lands. But now, what if you could fire it at a precise, mind-boggling speed? What if you could fire it so fast that as the cannonball falls toward the Earth, the spherical surface of the Earth curves away from it at the exact same rate? The cannonball would now be continuously falling, but it would never get any closer to the ground. It has entered an orbit. It is in a state of perpetual freefall. This is precisely what the International Space Station and all the satellites that circle our globe are doing. They are not floating in a region with no gravity. In fact, at their altitude, the pull of Earth's gravity is still about 90% as strong as it is on the surface. And the reason astronauts experience weightlessness is because they and everything inside their spacecraft are all falling together. They are all like the cannonball, constantly falling towards the Earth but moving seaways so fast that they always miss. It's a continuous, graceful, high-speed fall that traces a circle around our planet. It is the perfect balance point, a place where the forward momentum of the spacecraft is perfectly matched by the constant inward pull of gravity, creating a stable, weightless dance in the quiet of space. This delicate, weightless dance of an orbit is a triumph of our understanding. It's a precise and predictable ballet, governed by the laws of gravity that we have come to know so well. We can calculate the path of a satellite, the journey of a probe to another planet, and the constant fall of our moon around us with incredible accuracy. For a long time we thought we had a fairly complete picture. We believed that if we could measure all the visible things in the universe, the stars, the gas, the dust, we could understand its structure. But when our instruments became powerful enough to look beyond our immediate neighbourhood, to study the grand dance of entire galaxies, we discovered a profound mystery. We found that the universe, it seems, has a secret, a hidden component that outweighs everything we can see by more than 5 to 1. The story of this discovery begins in the 1960s and 70s with the work of a brilliant and tenacious astronomer named Vera Rubin. She was studying the rotation of spiral galaxies, beautiful stellar cities very much like our own Milky Way. Using the laws of gravity laid down by Newton and refined by Einstein, she had a clear expectation of what she should find. In a system held together by gravity, like our solar system, the objects further from the central mass move more slowly. Mercury, closest to the Sun, zips around at high speed, while distant Neptune plods along on its vast, slow orbit. Gravity's grip weakens with distance, so orbital speed must decrease. Vera Rubin expected to see the same thing in galaxies. The stars near the bright, dense galactic centre should be moving quickly, while the stars on the far, dim outskirts should be moving much more slowly. She pointed her telescope and began to measure, and what she found was astonishing. It was something that simply should not be. The stars on the outer edges of the galaxies were moving just as fast as the stars near the centre. This was deeply strange. It was as if Neptune were orbiting our Sun at the very same speed as Mercury. If that were the case in our solar system, Neptune would have flung itself out into interstellar space long ago. The Sun's gravity simply wouldn't be strong enough to hold on to it. By all rights, these fast-moving outer stars should have been breaking free from their galaxies, flying off into the void. The galaxies themselves should be tearing themselves apart. Yet they were not. They were stable. They were holding together. The only way this was possible was if there was a tremendous amount of extra gravitational pull, a pull coming from mass that nobody could see. After painstakingly checking and rechecking her data, the conclusion became inescapable. The galaxies were filled with and surrounded by a vast invisible halo of some unknown substance. A substance that has mass and therefore has gravity, but gives off no light, no heat, no radiation of any kind. It was given a simple yet profoundly mysterious name: dark matter. The dark in dark matter doesn't mean it's the colour black. It means it is utterly transparent to all forms of light. It doesn't shine, it doesn't reflect, it doesn't even cast a shadow. It is completely, totally invisible. The only way we know it's there is by its gravitational influence on the things we can see, like the spinning of those distant stars. Scientists have spent decades trying to figure out what this mysterious substance could be. We know what it is not. It is not just vast clouds of cold gas or dust that we haven't detected yet. It's not countless dead stars or black holes. Astronomers have done the accounting, and while those things exist, they don't add up to nearly enough mass to explain the discrepancy. The leading hypothesis is that dark matter is something truly exotic. It is likely made of a new type of fundamental particle, a particle that is not part of the standard model of physics that describes the protons, neutrons and electrons that make up you, me, and everything we've ever touched. This particle would be a kind of cosmic ghost. Billions of them are likely streaming through your body, through the very room you're in, and through the entire Earth right now, but they don't interact with ordinary matter in any way. They pass through us as if we weren't even here. They feel only the force of gravity, and perhaps one other fundamental force we don't yet understand. It is a silent, invisible ocean in which our galaxy is but a swirl of luminous foam. And so we find ourselves in a universe far stranger than we had imagined. Our galaxy is not just an island of stars, but a luminous eddy in a vast invisible ocean of dark matter. This substance, this cosmic ghost, provides the extra gravity needed to hold our stellar city together. It is the unseen scaffolding upon which the visible universe is built. For billions of years, gravity, aided by its mysterious dark companion, was the dominant force of cosmic construction, pulling matter together to form the magnificent structures we see. It seemed, for a time, that the ultimate fate of the universe would be a simple tug-of-war between the initial outward momentum of the Big Bang and the constant inward pull of gravity from all the matter, both light and dark. Scientists thought the expansion of the universe must be slowing down. Gravity was acting as a cosmic brake. The only question was whether the universe had enough mass to eventually halt its expansion and fall back in on itself in a big crunch, or if it would slow down forever, expanding into a cold, dark future. To find the answer, in the late 90s, two separate teams of astronomers set out to measure this cosmic deceleration. Their method was both ingenious and beautiful. They used distant, exploding stars, a specific kind of supernova, as cosmic lighthouses. These particular supernovae are what's known as standard candles. They all explode with nearly the same intrinsic brightness. So like knowing the wattage of a light bulb, if you can measure how dim one of these supernovae appears to us, you can calculate precisely how far away it is. The astronomers pointed their telescopes to the deepest, most ancient corners of the cosmos and began to hunt for these faint, fleeting explosions. Their goal was to map the history of the universe's expansion. They measured the distance to the supernovae, and they measured how fast they were moving away from us. They expected to find that the more distant supernovae from the universe's youth were moving away faster than the closer ones. They expected to see the signature of a universe that was slowing down. But that is not what they found. Again, the universe delivered a surprise so profound it would shake the very foundations of cosmology. The most distant supernovae were consistently dimmer than they were supposed to be. They were farther away than all our models predicted. The only way to explain this was if sometime in the last few billion years, the expansion of the universe had stopped slowing down and started speeding up. The implications of this were staggering. It was like throwing a ball into the air and watching it fall for a moment, only to then see it suddenly accelerate upwards, faster and faster towards the sky. Some unknown force was at work, some kind of anti-gravity, inherent in the very fabric of space itself, was pushing the universe apart. This mysterious influence was given a name that echoes its enigmatic cousin, dark energy. It is crucial to remember the difference between these two great unknowns. Dark matter is gravitationally attractive. It clumps together, pulling matter with it to form and hold galaxies. Dark energy, on the other hand, appears to be gravitationally repulsive. It is smooth and distributed evenly everywhere in space. It does not clump. It is a gentle, persistent pressure that is causing space itself to expand at an ever-increasing rate. What could it be? The leading idea takes us back once again to Albert Einstein. When he first formulated his theory of general relativity, the prevailing wisdom was that the universe was static, neither expanding nor contracting. To make his equations work in a static universe, he had to add a new term, a cosmological constant, which acted as a repulsive force to counteract gravity's pull and hold the universe in perfect balance. When Edwin Hubble later discovered that the universe was in fact expanding, Einstein discarded the idea, famously calling it his biggest blunder. And yet, in one of science's most wonderful ironies, he may have been right for the wrong reason. This dark energy may well be the cosmological constant he imagined. It may be an intrinsic, fundamental property of the vacuum of space itself. It suggests that even the most perfect emptiness is not truly empty. There is an inherent energy to space-time, a baseline cost for existing that manifests as a negative pressure, pushing everything apart. For the first 9 billion years of the universe's history, the pull of gravity from matter and dark matter was stronger. But as the universe expanded and matter became more dilute, the constant, unwavering push of dark energy eventually took over. And now, it is the dominant force in the cosmos, pushing galaxies away from each other into a future of accelerating isolation. So our universe is a grand stage, with two mysterious actors driving its ultimate fate. Dark matter, pulling the cosmic web together, and dark energy, pushing the voids apart. It is a gentle, slow-motion drama playing out over billions of years and across unimaginable distances. But what happens when gravity is not just a participant in a cosmic tug-of-war? What happens when it is allowed to win, absolutely and completely? To find the answer, we must journey from the largest scales of the universe to the most extreme, the most compact and the most mysterious objects within it. We must drift towards a black hole. Let's return to the life of a star. As we've explored, a star is a delicate balance. The outward pressure of nuclear fusion in its core holds back the relentless inward crush of its own gravity. Our sun is in this stable phase, and will be for billions of years to come, but for stars far more massive than our own, the end of life is much more dramatic. When these stellar giants exhaust the fuel in their cores, the outward pushing furnace goes out. Suddenly there is nothing to oppose the force of gravity. In a fraction of a second, the star's core collapses in on itself. The weight of the star's outer layers comes crashing down, squeezing the core to an impossible density. This catastrophic implosion can trigger a supernova, blasting the star's outer layers into space in a brilliant, beautiful display. But for the core itself, if it is massive enough, there is no force in the universe strong enough to stop the collapse. It just keeps going, crushing itself, smaller and smaller and smaller. As the matter collapses, the density and the gravitational pull become extreme. The fabric of space-time, which we pictured as a gently curved trampoline, is now warped into an infinitely deep well. As the object shrinks, the escape velocity from its surface skyrockets. Eventually, the collapse reaches a point of no return. A boundary is formed in space. This boundary is not a physical surface you could touch, it is a threshold. It is the point where the escape velocity has become equal to the speed of light. We call that boundary the event horizon. Since the laws of physics as we know them state that nothing can travel faster than the speed of light, anything that crosses the event horizon can never leave. Not a spaceship, not a planet, not even a beam of light. It is a one-way door in the universe. Any light emitted from within this boundary is immediately pulled back, unable to escape. This is why we call it a black hole. It has been cut off from the rest of the observable universe, a region of space that can pull things in, but from which nothing, not even information, can ever return. What lies at the centre of this object beyond the quiet veil of the event horizon? Our current theories predict something our minds can barely grasp, a singularity. All the mass of the collapsed star and anything else that has ever fallen in is crushed into a single point with zero volume and infinite density. Now, whenever a theory in physics gives us an answer of infinity, it's usually a quiet signal that the theory itself has broken down. It is pointing towards the edge of our knowledge. General relativity, the theory that describes gravity and black holes so well, is a classical theory. It doesn't include the strange and wonderful rules of quantum mechanics, the theory that governs the universe at the smallest of scales. Most physicists believe that at the heart of a black hole, these two great pillars of modern physics must meet. To truly understand the singularity, we would need a new theory, a theory of quantum gravity, which could describe how space-time behaves under such extreme conditions. We are still searching for that theory. The singularity is a placeholder for a deeper truth we have not yet uncovered. The extreme warping of space-time near a black hole also has a profound effect on time itself. As we touched on before, gravity slows down time. Near an event horizon, this effect becomes almost infinite. If you were safely watching a friend journey towards a black hole, you would see something extraordinary. As they got closer to the event horizon, you would see their clock, and all their movements begin to slow down. They would seem to be moving in ever slower motion, their image becoming redder and dimmer, until they appeared to freeze, suspended at the edge of the horizon for all eternity. From their perspective, however, time would feel perfectly normal. They would simply cross the event horizon in a finite moment, unaware of the time-bending spectacle seen by the outside universe. It is one of the deepest and most wondrous paradoxes of relativity. The singularity at the heart of a black hole, much like the very first moment of the Big Bang, represents a frontier. It is a place where our most powerful and elegant theory of gravity, Einstein's general relativity, gracefully bows out and admits its own limitations. It gives us an answer of infinity, which is nature's way of telling us, look deeper. There is another layer to this story. That deeper story is the greatest quest in modern physics, the search for a single, unified theory that can describe the entire universe. For the past century, physics has rested on two colossal pillars. The first is general relativity, the theory of the very large. It is a theory of smooth-flowing space-time, of planets in their elegant orbits, of expanding galaxies and collapsing stars. It is deterministic and geometric, a vision of the universe as a grand cosmic architecture. The second pillar is quantum mechanics, the theory of the very small. It is the rulebook for the world of atoms and particles. It describes a universe that is not smooth but grainy, or quantized, where energy comes in discrete packets. It is a world governed not by certainty, but by probability, and a constant jittery dance of potential. Both of these theories are stunningly successful. They are the most accurate and well-tested theories in the history of science, yet they speak fundamentally different languages. They are like two magnificent symphonies playing in different keys. In most of the universe, this doesn't matter. Relativity governs the stars and quantum mechanics governs the atoms within them, and that they rarely need to interact. But in the heart of a black hole, or at the dawn of time, the very large becomes the very small. An entire star is crushed to a quantum dot. And here the two theories collide. Here, we need a new kind of music. The search for this new music, for a theory of quantum gravity, is the search for a single framework that can unite these two pillars. A theory that can describe all of nature's forces as different aspects of one single, underlying reality. Many brilliant minds have dedicated their lives to this search, and while the final answer remains elusive, there are promising and beautiful ideas. Perhaps the most well-known of these is string theory. It proposes a breathtakingly elegant and simple idea. At the most fundamental level of reality, the particles we see are not little points or spheres. They are unimaginably tiny, one-dimensional, vibrating loops of energy. They are like the strings on a cosmic cello. And just as the vibration of a cello string determines the musical note you hear, the specific vibrational pattern of one of these fundamental strings determines the particle you see. In this vision of the universe, a string vibrating in one way appears to us as an electron. A different vibration looks like a photon, the particle of light. Another, a quark. All the matter and forces we see are just different notes being played in a grand cosmic symphony. And crucially, the theory predicts one particular vibration that has the exact properties of the graviton, the long sought-after quantum particle that would carry the force of gravity. In string theory, gravity is not separate from the other forces. It is simply another note in the universal song. This quest also brings up a simple yet profound question. Why is gravity so weak? It may seem like the most powerful force holding planets and stars in its grip, but it is, by an enormous margin, the weakest of nature's forces. A simple refrigerator magnet, using the force of electromagnetism, can lift a paperclip, completely overwhelming the gravitational pull of the entire Earth. String theory offers a wondrous, if speculative, explanation. It suggests that our universe may have more dimensions than the three of space and one of time that we experience. Perhaps gravity seems so weak because, unlike the other forces which are confined to our dimensions, gravity can leak into these other hidden dimensions, diluting its strength. It would be like seeing the ripples from a stone dropped in a pond, but only being able to perceive a tiny fraction of their true energy. So tonight, as we rest on the edge of sleep, we can reflect on this journey. We began with the simple, reassuring feeling of gravity holding us in place. We followed that feeling out to the moon, the planets, the distant stars. We saw how it builds worlds and shepherds galaxies. We encountered its mysterious sea in the invisible scaffolding of dark matter and the repulsive energy of the void. We journeyed to its most extreme point, the silent horizon of a black hole. And now we find ourselves at the edge of our own understanding, listening for a new, deeper music in the fabric of reality. The simple, familiar force of gravity is also our greatest puzzle, a quiet invitation to keep wondering. Tonight we have journeyed far together, all while resting quietly in our own peaceful spaces. We started with the simple grounding feeling of our own weight, the gentle but firm embrace of the earth. We saw how that simple feeling is a connection to a universal law, one that dictates the graceful dance of the moon and the planets. We followed this idea deeper into the very fabric of reality, picturing space-time itself, curving and shaping our path through the cosmos. We watched as gravity, this patient and silent architect, gathered dust into stars and stars into the great luminous cities we call galaxies. We felt its influence in the rhythmic breathing of our oceans and in the very structure of our bodies, which have grown strong against its constant presence. We drifted into the great cosmic twilight, pondering the invisible pull of dark matter that holds our galaxy together, and the even more mysterious push of dark energy that is gently guiding the universe toward an accelerating future. We stood at the edge of the ultimate abyss, the event horizon of a black hole, where space and time themselves come to an end. And we listened for the first faint notes of a new cosmic symphony, a unified theory that might one day sing the complete song of the universe. Through it all, from the fall of an apple to the warping of space-time, gravity has been our constant guide. It is the force of connection. It connects you to the Earth. It connects the Earth to the Sun. It connects our Sun to the billions of other stars in the Milky Way. And it connects our present moment to the very first moments of creation. The iron in your blood was forged in the heart of a star that collapsed under its own gravity. The planet you are resting on was gathered by this same patient force. You are right now a collection of stardust, held together by the laws of the universe, peacefully following a path through the curved space-time of our solar system. Thank you for joining me on this quiet exploration. If you enjoyed our time together and feel a little calmer, a little more curious, I would be so grateful if you considered leaving a gentle like, or perhaps even subscribing for our future journeys. It truly does help more sleepy minds find their way to this little corner of peace. May you feel safely and comfortably held tonight. May your rest be deep and untroubled, and may your dreams be filled with quiet wonder. Sleep well, and until next time, keep wondering.